Here's the original design of our Mousetrap car with 4 records as our wheels, and we changed this plan so the car would be more likely to start without hesitating.
Here's the improved design of our Mousetrap car with 2 records in the back and 1 CD in the front. We changed our original design to make the car start better and to improve the angle.
Yeah, I can feel it in the air that it's on tonight. I don't really care if it's wrong or right. Better to the metal.
On the first day of work, we decorated the car by spray painting the CDs in balsa wood. On these days, we added the CDs to the records and then these new wheels to the axles and balsa wood. On these days, we realigned the balsa wood so that they would be more balanced on the axles and also glued down the wooden connectors. Day 6, we attached the Mousetrap to the car with hot glue and then the wooden dowel and string to the Mousetrap with zip ties. Now that our car was built, we began to make adjustments so that it would move on its own. To do so, we increased the surface area of where the string would be wrapped around on the axle, and the car began on its own and continued to move at a good pace.
See, our wheels are so bad. Hey, we love the speed bump. Okay, let's see if the launch works. Oh my gosh, go. Nope.
On day 9, we added cut wooden dowels near the pole and the Mousetrap so that the wooden dowel would not hit the wheels or the ground, stopping the movement of the car. On day 10, we replaced the Mousetrap on our car with another one so the spring would be newer, but later that day it broke, so we had to replace it again. On day 11, we tested our car 2 more times to make sure it was ready.
30 seconds!
Are we almost good?
Alright, here we go. New song. Keep going. Come on. 19, 20 seconds. Come on, come on, come on.
Rolling through your town. Saying all the windows down. When I'm rolling.
Ready?
That is the name.
One. Countdown. Countdown.
Okay, so the 1, 2, 3, go. Okay. Go as fast as possible.
Have mercy on me!
Forgive us our sins.
Does this one count?
I think God blessed it today.
Two types of friction we used in this project was static friction and rolling friction.
Like you, always want back.
At first, our car would not start because of static friction. To improve the car so it would start, we tested the car on a very smooth surface rather than the carpet, and increased the circumference of the back axle of our car, so the input force would multiply to a greater output force.
We used 2 records for our back axle and 1 CD for our front axle. We used 2 records because the wheel's resolution is greater than that of a CD.
Now you say you want it back. Now that it's just too late. Well, could have been easy. All you had to do.
We incorporated Newton's first law because the Mousetrap is the force that moves our car. It continues to move the lever at a constant speed as the car glides across the floor.
Here you are now, calling me up, but I don't know what to say.
Second law relates to our car because the lighter the mass is, the easier it is to start the car. For this reason, we made sure that the body of our car was light, and we did this by making it hollow and out of light wood, which was balsa wood.
Goodbye. Hey, all you had to do was stay. Held me in the palm of your hand. Then
Third law is related to our Mousetrap car because when you pull back the lever and wind the string around the back axle, the car gains potential energy. So if you wind the lever all the way back, it can go the full possible distance, and if you only wind it 50% of the way, it can only use 1/2 of its potential distance.
If the lever arm is shorter, less string is used so the axle doesn't rotate as many times. The longer the lever, the more total mass the car has, decreasing the acceleration and making it move slowly.
When the center of the wheel is properly positioned and stable, the wheel should allow the axle to rotate. It will also make the car go straight. The challenges that we faced in our car were that the wheels wobbled. We tried to help this by using stoppers to hold the wheels in place. We also struggled to get our car to start, so we increased the circumference of the back axle. The lever also wasn't very stable, so we tightened the zip ties as much as possible and used part of a wooden dowel to make sure that the dowel would not hit the ground or the front wheel when it fell all the way.
Here is a diagram of the different forces that affected the movement of our Mousetrap car. The potential energy is in the spring of the Mousetrap car, so when we wound back the string and the pull, the car is ready to be released and move. The potential energy later becomes kinetic energy as the lever arm lifts, causing the Mousetrap car to move. Some energy of this is friction though.
Our car moved 8 meters in 19 seconds, and we converted this to miles per hour to find that the average speed of our car was 0.89 miles per hour.
If the lever arm is shorter, less string is used so the axle doesn't rotate as many times. The longer the lever, the more total mass the car has, decreasing the acceleration and making it move slowly.
Incorporated in our Mousetrap car were the wheel and axle and a lever. The lever was 86 centimeters long, and we calculated that the mechanical advantage of our lever was 1. The wheel and axle had a radius of 15 centimeters, and the radius of the axle is 0.254 centimeters. And the radius of the large wheel divided by the radius of the axle was 59, which was our mechanical advantage. I don't think that. The power of our car was 1.45 watts, and we found this by doing work divided by time, and the formula for work is force times distance.